Welcome to an instructive video by Duro-Sense titled Key Principles to Accuracy in Temperature Measurement. Key Principles to Accuracy in Temperature Measurement. Extremely accurate temperature measurement is possible through the use of suitably calibrated sensors and instrumentation. The accuracy of these measurements, however, won't mean anything unless the sensors and equipment are used correctly. Thermocouples are the most widely used and versatile pieces of equipment used to measure temperature. They are rugged, reliable, and can function over a wide range of temperatures. Careful selection of thermocouples can ensure accurate sensor performance. Thermocouple accuracy can be defined as the amount of error that exists in its temperature measurement. It can show how close the value of the measured temperature of a given thermocouple is compared to the true temperature value. This is referred to as the tolerance or the error. The table Initial Calibration Tolerances, Fig. 1, shows us what accuracy or tolerance can be expected from each particular type of thermocouple. Thermocouple accuracy is affected by several factors including the type of thermocouple, the temperature range of the thermocouple, the process used to manufacture the thermocouple, the purity of the material used to make the thermocouple, as well as external factors such as corrosion, degradation of the junction, electrical noise. Thermocouples are typically available in two tolerances, standard limits of error and special limits of error. In the United States, the standard that most commonly controls accuracy is ASTM E230. As can be seen in these tables, thermocouples with special limits of error tolerances have higher accuracy than thermocouples with standard limits of error tolerances. Applications where accuracy is one of the critical factors would typically use special limits of error thermocouples. The table in Figure 1 is easy to use. To determine the initial accuracy of a thermocouple, you ascertain the greater of the two tolerances given. Example, a type K thermocouple is heated to 800 degrees Fahrenheit. What is the tolerance at this temperature? We can see from the table in Figure 1 that it is plus or minus 0.75%. To calculate the thermocouple accuracy, simply multiply the tolerance by the temperature. 0.75% times 800 equals 6.0. Therefore, at 800 degrees Fahrenheit, the accuracy of a standard limits of error type K thermocouple is plus or minus 6.0 degrees Fahrenheit. Using the same formula, let's look at the accuracy of the same thermocouple under special limits of error tolerance. We can see from the table in Figure 1 that the tolerance is plus or minus 0.4%. To calculate the thermocouple accuracy, simply multiply the tolerance by the temperature. 0.4% times 800 equals 3.2. Therefore, at 800 degrees Fahrenheit, the accuracy of a special limits of error type K thermocouple is plus or minus 3.2 degrees Fahrenheit. Every process in which we need to measure temperature is different. Some require a high degree accuracy and some do not. When selecting the proper measuring equipment for your process, it is important to understand the accuracy requirement. Basically, temperature measurement requirements can be categorized into two groups. 1. The process does not require accuracy. You simply need to know if the temperature is stable or moving up or down. And 2. The process does require a high degree of accuracy. This report will focus on those processes that require a high degree of accuracy and how to mitigate issues that could compromise the accuracy of your process. The following characteristics can help to ensure accurate sensor performance. Sensor type. This may seem obvious, but it is surprising how often the wrong thermocouple is used, either because that was all that was available at the time or through a lack of understanding of the parameters of the sensor. For most applications operating at 1400 degrees Fahrenheit or 760 degrees Celsius or less, any of the base metal sensor types, K, J, T, E, and N, will work, but they all have unique attributes that differentiate them from each other. Type K, the most common type of thermocouple. It's inexpensive, accurate, reliable, and has a wide temperature range. Works well in oxidizing and inert atmospheres up to 2,300 degrees Fahrenheit or 1,260 degrees Celsius. Is often used at temperatures above 1,000 degrees Fahrenheit with better oxidation resistance than types J, T, and E. However, can be subject to green rot corrosion in low oxygen environments at temperatures above 1,500 degrees Fahrenheit. Not recommended for use in reducing atmospheres or atmospheres that alternate between reducing and oxidizing. Not recommended for use in sulfurous atmospheres or under vacuum conditions. Type J, also a common type of thermocouple. It has a lower temperature range and a shorter lifespan at higher temperatures than the Type K. It is equivalent to Type K in terms of expense and reliability. It works well in the widest range of environments, including oxidizing, reducing, inert, and vacuum atmospheres over its temperature range of 32 to 1400 degrees Fahrenheit or 0 to 760 degrees Celsius. However, above 1000 degrees Fahrenheit or 538 degrees Celsius, the iron leg is susceptible to rapid oxidation, and below 32 degrees Fahrenheit or 0 degrees Celsius, the iron leg can experience rusting and embrittlement. Type T, very stable and preferred for low-temperature applications, including cryogenics, minus 330 degrees Fahrenheit or minus 201 degrees Celsius. It is resistant to corrosion in damp atmospheres. However, in air or oxidizing atmospheres, oxidation of the copper legs can occur at temperatures above 700 degrees Fahrenheit or 370 degrees Celsius. Type E has a higher accuracy and stronger signal than the Type K or Type J at moderate temperature ranges of 1000 degrees Fahrenheit and below. It also exhibits the highest sensitivity of the other base metal types and is often chosen for this reason. It functions well in a wide temperature range from minus 330 to 1600 degrees Fahrenheit or minus 201 to 870 degrees Celsius in inert or oxidizing atmospheres. It is resistant to corrosion in high moisture environments. Not recommended for use in reducing or vacuum atmospheres. Type N shares the same accuracy and temperature range as Type K. It is slightly more expensive, but as time goes on, it is becoming more popular as a replacement for Type K. It isn't affected by some of the idiosyncrasies of Type K, such as order-disorder temperature drift or green rot. Type S is used in very high temperature applications. Recommended temperature range is 1000 to 2700 degrees F or 538 to 1482 degrees C. Conductors are platinum and rhodium. It is sometimes used in lower temperature applications because of its high accuracy and stability. As a noble metal thermocouple, it is the best choice for long-term accuracy and repeatability at very high temperatures. Protection from all atmospheres must be provided, as it is subject to contamination and drift. Prolonged use at high temperatures can cause grain growth, which can lead to mechanical failure. Type R is also used in very high temperature applications. Recommended temperature range is 1000 to 2700 degrees F or 538 to 1482 degrees C. Conductors are also platinum and rhodium, but it has a higher percentage of rhodium than the Type S, which tends to make it more expensive. It is very similar to the Type S in terms of performance. It also must have protection from all atmospheres, as it is subject to contamination and drift. Prolonged use at high temperatures can cause grain growth, which can lead to mechanical failure. Type B is also used in extremely high temperature applications. It has the highest temperature limit of the three platinum and rhodium thermocouples. Recommended temperature range is 1600 to 3100 degrees F or 871 to 1705 degrees C. It is used in similar applications as Type S and Type R, but with better accuracy and stability at very high temperatures. It is also less susceptible to grain growth and drift. Type C is also used in extremely high temperature applications. Conductors are tungsten and rhenium. It has the highest temperature limit of all of the thermocouples listed above. Recommended temperature range is 1000 to 4200 degrees F or 538 to 2315 degrees C. It must be used in vacuum or inert atmospheres because it has no oxidation resistance. Exposure to oxidizing atmosphere will cause immediate failure. In addition to the thermocouple type, careful selection of the sheath material and insulating material is critical in order to avoid any interaction between conductors and the other elements of the assembly. Be sure to provide all pertinent details about your application environment to your thermocouple manufacturer to ensure the best assembly is chosen for your unique application. Manufacturing process. Another factor is ensuring accuracy in your temperature measurement is the manufacturing process. Errant readings, Intermittent signals, large offsets, and poor insulation resistance can all be attributed to poor fabrication practices. You should use a manufacturer who adheres to recognized quality standards in production, testing, and quality control. They should maintain clean and organized work areas and provide evidence of these processes upon request. Proper immersion length. A common error made when configuring a thermocouple is using the wrong immersion length. The preferable immersion depth is one that is a minimum of 7 to 10 times the outer diameter of the thermocouple sheath. This will alleviate a condition called stem conduction. This refers to unwanted heat transfer up the metallic sheath of the sensor. In an application where the sensor is inserted into a pipe, the thermocouple should be inserted into the process a minimum length equal to 1/3 the inside diameter of the pipe. The ideal insertion depth should be at the center of the pipe diameter. When calculating the distance to the center of the pipe, be sure to account for the wall thickness of the pipe and any mounting hardware. Using the thermocouple at the incorrect immersion depth can have a direct impact on the accuracy of your readings. Response time. The mass of the sensor material is a direct relationship to the speed of the sensor's response. Lower mass will produce a faster response, while a larger mass will produce a slower sensor response. Most furnace and oven applications have generally benign environments that do not require massive elements. This is particularly important to consider during thermal ramp-up and cool-down, as excessive mass will hamper the sensor's ability to respond adequately to the rapidly changing temperature. Cold junction compensation. The science behind a thermocouple shows the junction between two dissimilar metals generates a voltage, and this voltage is a function of temperature. Unfortunately, one cannot simply attach a voltmeter to the thermocouple to read the voltage. This creates a secondary junction. To take accurate measurement of this voltage, one must employ what is known as cold junction compensation, or CJC. All standard thermocouple tables and modern instrumentation account for this in their calculations. Typically, the temperature at the hot junction is recorded. Then the point where the wires connect to the measuring device is recorded. This second reading, coupled with the first reading, is used by the recording instrument to calculate the actual temperature of the sensor. Understanding cold junction compensation is very important because any error introduced when measuring the temperature at the cold junction will lead to the same error in the temperature measured at the thermocouple hot junction. Therefore, on a side note, avoid exposing the thermocouple cold junction connections to abrupt changes in temperature. That is, hot or cold air currents, proximity to extreme warm or cold temperatures, etc., as this will impose error in your readings. Degradation or decalibration. This situation can occur when the makeup of the thermocouple is unintentionally altered. The typical cause of this phenomenon is the diffusion of elements in the atmosphere into the material from which the thermocouple is made, that is, oxidation, corrosion, contamination, etc. This can also be caused by a number of other factors, including impurities in the insulation around the conductors migrating into the wire, loss of wire alloying components, and an interaction between the components of the assembly, conductors, insulation, sheath material. All of these circumstances will work against accuracy in your readings. The degree of degradation depends on the environment inside the process and the purity of the materials used to fabricate the thermocouple. Therefore, it is good practice to check the specification of the materials, especially if the thermocouple will be operating at high temperatures. In addition, whenever possible, it is advisable to use thermocouples with insulated junctions. This will aid in protecting the conductors from contamination. Interference or noise. Output signals from thermocouple are measured in very low levels of MV. Motors, variable frequency drives, radios, and other devices, as well as stray magnetic and electrical fields, create normal levels of electromagnetic interference and radio frequency interference that tend to measure much higher. Therefore, it will not take much noise to significantly disrupt or distort these signals. This can cause significant errors in accuracy. Best practice suggests minimizing the noise where possible. This can be achieved using several simple practices. First, use an isolated or ungrounded junction. This will help to isolate the MV signal from the external noise. Second, if running lead wires near noise sources, such as power lines, conduit containing electric wiring, or other magnetic field generators, the lead wires should be routed away from these sources. If they must run adjacent, route them across perpendicular and not parallel to these power sources. Whether they run in close proximity or not, the use of shielded cable will also help isolate your MV signal from the external interference. Calibration thermocouples can remain stable for extended periods of time at elevated temperatures in benign conditions. However, due to several factors, like those listed above, sensors can change calibration over the same time period. To minimize inaccuracy, periodically recalibrating the thermocouple is advised. An important fact to be remembered is that laboratory calibration of thermocouples is predicated upon good uniformity or homogeneity of the material used to fabricate the sensor being tested. New materials will possess this property, but used materials may not. Therefore, it is not uncommon for used sensors to fall out of tolerance during recalibration. This is particularly true for base metal types after use at high temperatures. Many times, when trying to achieve a desired accuracy, the focus is primarily on the thermocouple. Consideration must be taken of all the elements in the temperature measurement system. Combined, these elements account for a significant part of the total system accuracy. Therefore, wherever possible, thermocouples and recording and measuring instruments should be calibrated together as a system. Finally, while calibration in laboratory conditions can provide much less uncertainty, calibration in the actual location where the equipment is being used can be useful because the test is performed in the same conditions and configuration where it is used. The word calibration implies that a thermocouple can somehow be modified if it does not have a sufficient accuracy, or that recalibration can correct an error. This is a myth. Calibration of a thermocouple permits the user to know the exact error at a given temperature within the limits of uncertainty measurement. Calibration can be done at any temperature, but for true accuracy, it is always best practice to specify a smaller range of temperatures, especially if the temperature at which it will be used is a known constant. For example, if the temperature range in which it is being used is limited to 500 degrees F, then you should calibrate the material at this temperature. This will show you the error of the thermocouple at this temperature. Modern instruments typically allow you to enter an offset to compensate for the error in the sensor. This allows you to increase the accuracy and repeatability of your process. In conclusion, precision temperature measurement is possible through the use of well-specified and suitably calibrated instrumentation and sensors. However, the accuracy of these measurements will mean nothing unless the sensors and equipment are used correctly. Computer scientist and Naval Rear Admiral Grace Hopper once said, "One accurate measurement is worth 1,000 expert opinions." Author and entrepreneur Jim Rohn once said, "Accuracy builds credibility." Duro-Sense uses special limits of error, low drift, tight tolerance, and high accuracy materials exclusively in all of our products. Our proven track record and reputation for outstanding accuracy puts us at the forefront of precision temperature measurement. When you're ready to learn more about how Duro-Sense can help you solve your unique temperature sensing challenges and discover how much time, energy, and money we can save you, call us at 310-533-6877 or email us at sales@duro-sense.com.